So now we are going to talk about geometric series, where a geometric series is a series or a sequence of numbers where the first number is, let's say, 1 or 10 or any constant, and the subsequent numbers are a constant factor bigger than the previous number. For example, 1, 2, 4, 8, 16 is a geometric series, or 1, 3, 9, 27 is another geometric series, and so on. So the ratio of consecutive numbers is a constant. It could be bigger than 1, less than 1, it could be negative, it could be anything. But all that matters is the ratio of consecutive numbers is constant. And particularly, we are going to talk about in this problem a growing geometric series. So let's read the problem and let's understand what's going on here. So the Standard Charcoal Company has leased a coal mine for next 20 years. This mine is expected to produce coal worth $25 million per year. The operating costs of this mine start at $10 million per year and they grow 5% each year. So what is the total economic benefit to the company over the duration of the lease? Right, so this is where the geometric series is showing up in this problem, where so the operating costs start at a certain number, that is $10 million per year, and they grow 5% each year. So the next year's costs are going to be a constant factor bigger than today's operating costs, and so on. It just keeps growing every year, 5% each year. So if it was $100 this year, it is going to be $105 next year, and 105 times 1.05 in the next year, and so on. So let's see. So what are we supposed to do here? The total economic benefit to the company, which is the total profit or the total cost of or the total worth of the coal that is going to be produced over 20 years, which is straightforward. It is supposed to produce constant $25 million per year. So over 20 years, it will produce $500 million worth of coal. And the operating costs are slightly tricky. So the total operating costs over 20 years are not constant. They are slowly growing over time, and that's expected even in real life because of inflation, because of regulations, because of various reasons. So what is the total economic benefit to the company? So let's start with this. So total economic benefit, total benefit is total worth of coal minus total expenses. Let's call this equation 1. So total worth of coal, this is straightforward, which is 25 times 20. I'm dropping $1 million, which is $500 million. Now the tricky part is the geometric series part. So the total operating cost is going to be 10 in the first year, year 1, plus 10 times 1.05, because it grows at a rate of 5% every year. This is the cost in year 2, plus 10 times 1.05 times 1.05, because it grew by 5% in the second year over the end of first year. So this is year 3. I'm going to write one more term, plus 10 times 1.05, this is at the end of second year, plus or rather times 1.05 third year, times 1.05, this is the fourth year, and so on all the way to, I'm going to write the final term, 10 times 1.05 to the power 19. This is in the year 20. So that's this looks like we can do this numerically, but we want to see if there is a simple and easier way of approaching this, because if the number of terms is large, here it is only 20 terms, so maybe we can do this on a small calculator even, or definitely on a computer. But if the number of terms is large, or sometimes even the number of terms is infinity, which we can talk about later, then these sums may not be easily calculatable, or there could be numerical issues. So let's see how to in general solve the sum of a geometric series. So let's find sum of geometric series. So suppose we are given this series. Series is just a sequence of numbers. Let's say ar square, ar cube, ar to the power 4, and so on. Why am I writing plus here? It's just a comma. So this r is called common ratio, and a is just a constant. A is the first term. So the numbers are ar square. These are differing from each other by a constant multiple, and we want to calculate their sum. So let s be equal to this a plus ar square plus, that is ar to the power n minus 1. There is a total of n terms here. So we want to calculate this sum, and if we can find this sum, then it is easy to plug the numbers in our example above and find what is the total operating cost. So let's see. The way to solve this is, let's consider r times s, which is, I'm going to skip some space here, ar plus ar square plus all the way plus ar to the power n minus 1 plus ar to the power n. Each term is multiplied by r. So if we take the difference of these quantities, I'm going to subtract this. So this is going to be s times 1 minus r is equal to, all these cross terms will cancel. It's going to be a minus ar to the power n. So what do we have here? S is equal to a times 1 minus r to the power n divided by 1 minus r, which is also equivalently a times r to the power n minus 1 divided by r minus 1. Both forms are standard and both are used widely, and they are, as you can see, they are just equal to each other. Negative of the numerator divided by negative of the denominator. This form is usually used when r is less than 1, and this is usually used when r is greater than 1, but they are equivalent. You can see that they are the same equation. We like to have positive denominator, that's why people typically have these two different forms, but they are the same. So what do we have here? So now therefore, coming back to the original problem, total operating expense is going to be our a, the first term here. We have here 10 plus 10 times 1.05 plus 1.05 square and so on. So we have this equation 2 we have here is almost a geometric series in the desired form here. So a times r to the power n minus 1 divided by r minus 1. Here in our case, a is $10 million, r is 1.05, which comes to, so 10 times 1.05 to the power 20 minus 1 divided by 1.05 minus 1. So this is the sum of the geometric series, and I have calculated this sum. It comes out to be around how much was it? $330.65 million. So total benefit, we are getting it from equation 1. Here is our equation 1, which is total worth of the coal minus total expenses, which is $500 million minus $330.65 million, which is approximately $169 million. I'm not going to do the exact calculation here. All these numbers are all anyway approximate. So yeah, that's how we solve these kind of problems. That we have a geometric series, we recognize that it is a geometric series, and we can sum them using the geometric series summation formula. Or even if you don't know the formula, as long as you know how to derive it quickly, you can see that you multiply it by r, you subtract, and that's how you find the sum of a geometric series. And then it's easy to add or subtract once you have the numbers in closed form. And just a quick comment about, as I mentioned before, the infinite geometric series. So let's make a quick, so this is the final solution of the problem, but so let's talk about an infinite geometric series. So this almost always makes sense only when the case of common ratio being less than 1. So suppose I have a geometric series a ar square, ar cube, all the way, and I want to sum the series. So what that means is I want s is equal to a plus ar square plus all the way. There is no last term in the series. The series continues to infinity. So as you can, sorry, someone is calling me. As you can see, this series can only make sense if the terms are dying down fast enough. That is, if the numbers are growing, if r is greater than 1, then the series will explode. This terms are going to get bigger and bigger, and the summation will be infinite. But if r is less than 1, for the special case of r less than 1, we can use the formula that we had earlier, a times 1 minus r to the power n divided by 1 minus r, where n is actually infinity. This is the symbol for infinity, this one. So r to the power n, suppose r is equal to something less than 1, let's say half. Then n to the power infinity, which is r to the power infinity, which is 0. So this comes out to be a divided by 1 minus r. For example, if you are adding, say, let's take a quick example here. S is equal to 1 plus half plus 1 by 4 plus 1 by 8 plus 1 by 16 plus so on. Every term is half of the previous term, so our r is equal to half as in the previous example. And I want to add all these numbers, infinitely many numbers. So by the formula here, it will be a is the first term, which is 1 divided by 1 minus half, which is 2. So the sum of these numbers, where each number is half of the previous number, is 2 times the first number. And you can add many other different geometric series based on the common ratio. It only makes sense if r is less than 1, or in particular absolute value of r is less than 1 is all that we need. Sometimes the r can be negative. As long as the absolute value of r is still less than 1, we are fine. So yeah, that's about geometric series.